Hi folks, and welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to use specific heats to calculate temperature changes, or at least use specific heats in problems where temperature changes are relevant. So this problem is one I'm making up. It's kind of a follow-up to an example that I just did in one of my previous videos. In one of the previous videos I made, it was about making these things called cannonballs, and I calculated how much energy and time it would take to heat up, I believe it was 500 kilograms of lead, 500 pounds of lead it was, up to its melting point of 327 degrees centigrade. So now you can imagine, somebody's melted this lead, they've poured these cannonballs, and what they're going to do now is they're going to take these cannonballs, a bunch of them. Now, I don't know how many. That's what we're going to actually calculate here in a minute, N. I only drew 3 of them, but the idea is they're going to put these cannonballs into this tank of water. And what we're going to try to calculate is how many cannonballs we can put into this tank of water before the water goes from a starting temperature of 10 up to its boiling point of 100 degrees centigrade. That's the question we're going to be looking at. Now, the 10 degrees centigrade, this is coming from, if you take groundwater and put it in a tank, water should come out of the ground of around 50 degrees Fahrenheit, give or take, which I believe is around 10 degrees centigrade. All right. I've already written down some of the thermodynamic data we're going to need here. So over on the left here for lead has a specific heat of 448 joule per kilogram degree centigrade. We're going to assume these cannonballs start at a temperature of about 327. Over on the right, water has a specific heat of about 4186 joule per kilogram degree centigrade. And we're going to need this too. I wrote out the density of water is about 1,000 kilogram per cubic meter. This is the Greek letter rho, which is a common variable to describe density. And we're going to assume these cannonballs are about 5 kilograms each. So again, I've drawn 3 of them here, but really the number of cannonballs is unknown. Those 3 just represent some unknown number of cannonballs. We're going to imagine now that these cannonballs get put into the tank. Now, the level of the tank will go up, but that's just not an important part of this problem. We're going to assume that this tank is big enough to hold all of the water cannonballs and everything. Now, whenever you're working any problems in physics, basic assumptions should be stated. And there's a really important one here. How we define our system is important. So I'm going to define my system like this, kind of put a green border around it, right outside the edge of this tank. Okay. We're going to assume that no energy goes in or out of our system while this is occurring. And we're going to assume that the mass of the tank here is very small compared to the rest of the system and doesn't need to be considered. Right? So these are important assumptions for this problem. Now, are all those things exactly true? No. But, in physics, you always have to make simplifying assumptions, or almost nothing is calculatable. Or you can't get anything done unless you simplify things down. There's simplifying assumptions built into almost every calculation done in physics. And these are going to be the assumptions in this one. No heat transfer into or out of our system. The mass and thermodynamic properties of the system itself are not going to be significant compared to the water in the cannonballs. All right, so now we'll start thinking about equations here. The cannonballs are very hot, water relatively cool. So what we know is going to happen, I'm going to just kind of draw this maybe in red, is heat is going to transfer from the cannonballs to the water. Because the cannonballs are relatively hot, water is relatively cool. The cannonballs will drop in temperature, the water will go up in temperature. Now, the key factor here, though, is that while that occurs, again, go back to the system. If we define our system like this, no energy has went across that boundary, which means if we add up all the pluses and minuses, as far as the energy transfers are concerned, they should add to 0. So we can actually write an equation that says that. So I'll start with this. The heat transfer for the cannonballs, or I'll say the lead, plus the heat transfer for the water should sum to 0, and again, because of my discussion about no energy transfer across that green boundary. Now, for the lead, The lead's not going to have any phase change. The phase change for the lead really has already occurred because, again, they're solid. They're not liquid in this example. They're solid right at 327 or maybe, maybe 320, 325. Maybe they've cooled some, but they're right around that 327 degree mark. But the phase change has already occurred. That's not occurring because we're dumping them in here. So this term is going to be an MC delta T term. And delta T can be written T final minus T initial. And I'm going to put initial with an L on it for initial temperature of the lead. All right, and that comes right from how specific heat is defined. This specific heat, by the way, is the specific heat of lead. I should put that in the equation. Okay. The water is also going to come up in temperature now. So we're going to have a similar term for the water. Mass of the water, specific heat of the water, times T final minus T initial for the water. And there will not be any phase changes in this example based on the question that I've asked. The question we're looking for is how many cannonballs can we add to this to bring the water up to its boiling point of 100 degrees centigrade. But we're not going to be adding any more than that. So there will not be a phase change in this specific example either. All right. So these are the only two thermodynamic terms, and then equals 0. Okay. Next step here is to just go through, usually in problems like this, I like to put in the numbers first. Let's just kind of glance it over. Right? So this mass was for the lead, and I probably should put a little L on there for mass of the lead. Right? And that's something that we will get. We know it's 5 kilograms per cannonball. All we have to do is multiply by N the number of cannonballs. So we have something to put here. Specific heat is no problem. I've got that written to the left. The final temperature in this example is going to be 100. The initial temperature is 327 for the lead. So these are basically all known values. Mass of the water is not known yet. We're going to have to calculate that. Specific heat of water is 4186 joule per kilogram degree centigrade. And this T final minus T initial is going to be 100 degrees centigrade minus 10 degrees centigrade. So everything there is known except for the mass of the water. So the mass of the water we can get from the geometry of the tank here that I've written down. So I think I'll just do this off to the side. We can get this from density. Density is equal to mass over volume. Right? So mass can be written density times volume. And the density of water is about 1,000 kilograms per cubic meter. And what we'll do now is just multiply by the volume of the water in this tank. Now this is, looking down, this is a cylindrical tank. It's got a diameter of 1.5 meters and the water is 0.5 meters deep. So the volume is going to equal pi r squared times the height. And I'm getting that from the surface area of the tank times the thickness. The radius of that tank is going to be 0.75 meters because it's 1.5 meters in diameter. So what I'm going to do is right here I'm going to go ahead and put a volume term. Pi times the radius, which is 0.75 meters, and that's being squared, and then times this dimension, 0.5 meters. And what I'm going to do now is just wait here and ask one of my helpers here to calculate a value for me. 0.883, okay, times 2 of them, great, thank you. All right, so that's about 0.8, let's just do 0.88 cubic meters. I'm sorry, kilograms. Wait a minute. What'd you get again? 0.88. All right, I'm just going to pause this for a moment here and look that over. Something doesn't look quite right to me. All right, folks, sorry about that little glitch here. My helper gave me the volume and not the mass, which was fine. So what does that mass come out to be again? 883 kilograms is good enough. Actually, 880 kilograms is plenty good. Yeah, I had asked for it. Somebody gave me just the volume. And that was perfectly fine. I was just looking for the mass, and I knew that volume was a bit low. or I knew that mass was low. All right, so the mass of the water in this tank should be around 880 kilograms. So now what I'm going to do is go back to our thermodynamic equation here and just put in all the values that we have. So this was for the lead. Now we don't have a mass for the lead. What we know is that they're 5 kilograms per, and there's N of them. So the total mass can be written 5N. I'm also going to put NCU here for note consistent units. I don't think I'll have room in this equation if I try to write all the units out. So in the place of the mass, I'm putting 5N because it's 5 kilograms per times however many there are, times the specific heat of lead, which is 448. And again, I'm going to leave out the units, but joule per kilogram degree centigrade. They're sitting right here. All right, T final minus T initial is going to be 100 minus the initial temperature of the lead, which is 327, plus next term, mass of the water, 883 kilograms, times the specific heat of water, 4186 joule per kilogram degree centigrade. And then T final minus T initial is going to be 100 minus 10 equals 0. So what we have now is an equation here that can be solved for N. So I think what I'm going to do here is just pause and let my helpers take a minute and work on that. All right, folks, so I'm back here, and my crew here has calculated a value. So they get a value for N of approximately 650. So, you know, that's a lot of these 5 kilogram cannonballs. So let's talk a little bit about this and what this means. Well, first of all, I expected that number to come out pretty high, and I want to talk a little bit about why. First of all, we have 883 kilograms of water. That's a pretty darn big tank. And second, remember that water has a very, very high specific heat, 4186. And, you know, especially compared to lead, lead's specific heat's only around 448. So water's specific heat is 9, maybe somewhere between 9 and 10 times that of lead. So it's really difficult to budge the temperature of water, particularly using hot lead, because, you know, the lead doesn't hold as much energy per kilogram. So anyway, the reason that number came out so high is because, you know, we have a massive reservoir pool of about 883 kilograms, and we have a water which has a specific heat that's 4186 joule per kilogram degree centigrade. So I hope this example helped demonstrate these concepts. I think what I'll do is stop this right here and make up another one.